Good morning, everybody. Well, I can kind of say that. Now it's noon. No, I can't say that. Good afternoon, I have to say. Welcome back to Chemistry 131. Excuse me. Still have frogs in my throat because apparently all I do is eat cheese. My breakfast was cheese. Also bread and salami and stuff. Let me get the tablet out. I forgot to do that. I don't need this on my desk. There we go. Okay. So what are we doing today? We're going to do actual course content. Like, this is the stuff that you signed up for. So get ready for chemistry. Chapter 12 is our little intro. Oh, there's like all dust on my tablet here. Hold on. Like cat hair and stuff. So chapter 12, the first chapter that we're going to start with, this number corresponds to the online OER text that we are using, which has been linked in Canvas. If you can't find it, let me know. If you're using the recommended textbook, it's a different chapter. Do I have it in here? It's in the living room. I think it's chapter 11. It's the one that says unsaturated hydrocarbons or alkanes or something like that. These chapters are long at the start. Later on, we get to chapters that have similar amounts of content, but they aren't split into as many sections. So you can see the number of topics that we're going to cover in chapter 12 doesn't even fit on the screen. Like, it goes entirely off the screen. There's more stuff down there. Don't worry about this too much. I've sort of broken it up into baby steps to start. Let me know if you have any questions at any point, and I will answer them. But we're just going to go for as long as we can in chapter 12 in 2 hours, and we're definitely not going to finish it. I've allocated 6 hours for chapter 12. So let's get started. What the hell is organic chemistry? We've heard the word organic before, probably with regards to like produce. Like, you go to the store and there's the regular veggies section. And then there's the organic section. And the organic section is just more expensive. So maybe organic chemistry is just chemistry that's more expensive than regular chemistry. No, it's not really that. The term organic is thrown around in the world around us as meaning it comes from an organism. So that's kind of a stupid term. Like, that doesn't make any sense. Like, of course lettuce comes from an organism. Maybe that organism is called lettuce. But we have appropriated the term to mean, oh, we have grown this without extra stuff. It's organic. We don't use artificial fertilizers or herbicides or pesticides or other things like that. And there's a whole set of rules. I know somebody who worked in a fertilizer facility, which basically ended up being like he ground up fish all day. And that was used for organic fertilizer. And there were specific rules that his organization had to follow. So organic in the outside world beyond the scope of this class is kind of a mixed bag. It's kind of bullshit. For our purposes, organic means one very specific thing. And that specific thing has nothing to do with lettuce or even organic Coke, like whatever the hell that is. It doesn't mean any of these things. Let's just draw a big fat X through it. It's not these things. In reality, organic means it contains a specific element, and that element is carbon. An organic compound is a carbon-containing molecule. So the most common chemical that you come into contact with, water, is not organic. It doesn't have carbon in it. Water has hydrogen and oxygen. Carbon is weird in the sense that it has so much potential for bonding. And there are so many permutations of things it can do that we've developed an entire year of chemistry for it. We're going to condense that down into just like the simple stuff. We're going to show you a bunch of important molecules and then show you how those interact in the body for the biochemistry part. So what you're seeing in this class and in this section of organic chemistry is not going to be the complete picture, but you're going to wish that it was, because there's a lot to learn. And we're going to quickly establish a pattern as we go on. So organic chemistry is our understanding of all the compounds out there that contain carbon along with other elements, but they have to contain carbon. Those molecules, like all matter, undergo transformation when they interact with specific other entities. So, like, a certain compound of carbon might react with hydrogen, whereas this other one won't. We're going to learn all of the ins and outs so that we can see, oh, this type of molecule reacts with this type of molecule. And your job will be to generate this sort of giant flow chart. I'm going to show you sort of what we want to do as we go. I'm going to make one, and then it'll be up to you to make your own, because the flowchart that I will make, I don't really want to upload it, because then everybody will just use that, and then you won't learn from it. I will upload other things, but you'll see as the quarter goes on when we study reactions and molecule types and so on. All right, so those are our two criteria for this class. We have organic compounds, which have carbon, and inorganic compounds, which don't. Everything else that is not organic is inorganic. Now, this is what we're studying, but interestingly, this one is my degree. I did chemistry with the following elements. So I did platinum and uranium, which you might think, like, what the hell? And really, it was just, hey, they handed me these elements and was like, here, get to work. Here's some projects you can do. I was like, okay. But all of my chemistry also involved organic compounds. Is organic chemistry easier to teach? It's different. I don't really think I can compare the two equivalently, because it is so very different. I guess you'll see. Think about that question again in week 10, and I'm sure that you will know the answer by then. Like, wow, this is totally different. You might have an opinion on it. I personally don't have an opinion. I just think they're different. I think the best answer will be to just say, let's see. On the screen is a pencil. And you might think that a pencil is probably pretty straightforward, but it turns out that in the pencil, almost everything you see on the screen is organic. So let's just start by pointing at some stuff here. So pencil lead is not actually lead. It used to be made out of lead because lead is very soft. But lead is also super toxic. So we've now moved on to graphite, which is lighter and non-toxic. Graphite is just carbon. It's all these carbon-carbon rings and sheets stacked together in such a manner that they're very loosely attached by dispersion forces. And the result is when you rub pencil lead over paper, you leave a layer of that which you can see. And so you can use it to mark things. The wood of the entire pencil itself is cellulose. Cellulose is a carbohydrate. You'll notice that the word carbo here is where our carbon comes from. And then hydrate here, we've got H2O. And really what this means is H and O. When you think of hydrate, you should think of water. So a carbohydrate has carbon and hydrogen and oxygen in it. What about this eraser up here? An eraser is a polymer. Polymers are hydrocarbons that are strung together in a virtually endless chain of molecules, all connected together to make one big molecule. And that's it for the pencil. The metal is the inorganic part. So if you were to look around your room, if I was in a classroom, what I would say would be things like the table or desk you're sitting at is probably made of wood. Wood is cellulose, which is cell walls and stuff from trees. That's all organic. The chair you're sitting on is probably plastic. But if you're at home, it may be plastic or leather. Those are both organic. Leather coming from the hide of an animal. So it's skin or flesh, so that would be cells. Plastic being oil from dinosaurs that have been compressed over time. Your clothes are organic. They're made of like polyester or cotton or silk. They all contain carbon. Silk is actually special. It's a protein, so it contains more than just carbon. I mean, all of these contain more than just carbon, but proteins are special, and we'll talk about proteins later. But everything we interact with is virtually organic. Even the screen you're looking at probably right now has some organic chemistry in it. Not just the plastic frame, but maybe if you have OLEDs, you might have organic carbon compounds in there that are interacting with electricity to emit light, which is what you see when I draw on the screen. Or we'll give my little orc some tasks there. Now, organic compounds and inorganic compounds are very, very different in terms of their properties. Since we care about covalent compounds, we're going to talk mostly about these properties, but it is important to remember these too. Virtually, the opposite fact is true for an inorganic compound when you compare it to an organic compound. So, organic compounds are almost always covalent. They have very weak intermolecular forces compared to actual bonds like inorganic compounds. In like room temperature state, they are usually gaseous or liquid. There are some solids out there, and we'll talk about that a lot. Organic compounds are really flammable because they react with oxygen easily, and they're insoluble in water. As far as chemistry is concerned, chemistry with organic compounds is generally slow. For the reason that they have weak intermolecular forces, and we only get a reaction when molecules bonk into each other, or are at least attracted to the same vicinity and held there for some reason. We won't ever deal with conductivity, so I don't really care about it. But inorganic compounds have the opposite issues. So instead of having covalent bonds, they have ionic bonds. Remember that the difference between a covalent bond is that electrons are shared between two atoms in a covalent bond, so something like this, where there's no charge visible. Whereas in an ionic compound, the charges are isolated, and then the bond is formed from the attraction of those oppositely charged ions. Now, because all bonding has to do with charge, and those are visible charges that are present, ionic bonding is extremely strong. Whereas covalent bonding, the bonding itself is strong, but everything else around the molecule is a weak interaction. So, like, water is very strongly bonded to, like, the H's and the O are bonded all together in the molecule. But other water molecules are held together much, much more weakly than the bonds within water, as opposed to, say, NaCl, where every NaCl interaction is the same, and you have an ionic compound that is a zillion ions large in a lattice. So that's how you get all these different properties here. Now, when we talk about the physical properties of organic compounds, we're going to be looking back at these things. Can it bond with other molecules? Is it a solid, a liquid, or a gas? These two things are going to be related. If the stronger the forces are between the molecules, the more likely the substance we're looking at will be a solid. Is it flammable? The answer to that is always going to be yes. Is it soluble? This is going to depend very greatly on how polar the substances are. So solubility has to do with polarity. And so that's why we briefly went over polarity yesterday. All right, so what I'm going to do now is I'm going to put a problem on the screen, just like I did yesterday. I'm going to give you a problem for you to sort out. You can type your answers in the chat if possible. Obviously, later on, we're going to be drawing things, and that's going to be very difficult to put in the chat. But what I want you to do is tell me organic or inorganic for each compound, and then based on these properties down at the bottom, tell me if it's organic or inorganic. You can type your answers in the chat. You can communicate with each other. You can do however you want to. But I'm going to give you about 3 minutes to go over these questions, and then we'll go over the answers together in just a moment. It'll be really quiet during that time, so I give you time to work. All right, one more minute to go over the answers. Yeah, it is really weird to type in answers, and it's going to be extremely frustrating to input an answer in a lot of ways, especially when we start like typing in names of molecules, and this is going to be super long. Do the best that you can. If you make a Discord channel for the class, let me know so I can post the link on Canvas so that everybody has access to it. I will also join it. I don't want to be a moderator of any sort, though. I just want to be a member so that you guys can ask me questions after hours if you need to. Let's go over the answers here. Organic or inorganic? That answer is as simple as, does it have carbon? So here's a carbon and here's a carbon. Here's another carbon, but all we need is one. So these two are organic, but these two are inorganic. I can't spell. I'm actually very good at spelling, but my brain is not very good at writing. There we go. And then determine if the following are probably organic or inorganic. So we have to go back to that previous slide. Compound with a high melting point. High melting point means that the bonds are really strong. That's an ionic compound. Ionic compounds have really strong bonds. You have to put a lot of energy in to break those. Organic compounds don't have strong intermolecular forces, though. A compound that is flammable. Flammable means reacts with oxygen. That's organic. And then a compound that conducts electricity poorly. We didn't really give a shit about electricity, but this just happens to be organic. Organic compounds do not conduct electricity well. Now, just as a clarification, when I say they don't conduct electricity well, what I mean is relative to inorganic compounds. So water is kind of strange in that it doesn't conduct electricity super well, but it conducts it far, far better than, say, hexane or ethanol or things like that. And we won't really go into the why for that because that's kind of an Equilibria 163 issue. It has to do with how, electricity is just how many ions are available in the solution. And water has some ionic dissociation in there, but organic compounds have virtually none. All right, that's the first section. Let me know if there are any questions on these. Pretty straightforward. Let's talk about some organic compounds. So this is going to be the first real section. We're going to talk about alkanes. An alkane is just any compound that has only carbon and hydrogen in it. There we go. That's easy enough, right? So the first organic compound that we're going to care about has only two elements, and it only has two elements. So if you have anything else in there, it's something different. It's not an alkane. Now, how do we draw alkanes out on paper? Well, we're going to draw them Is conducting electricity poorly the same as usually slow chemical reaction? Conductivity and oops, sorry, I hit enter there. A chemical reaction are different things. So a slow chemical reaction is a different property than conducting electricity because electricity is a physical phenomenon. Excuse me. For example, if I plug something into the wall, I get the power from the wall outlet, which comes from the power company, without actually doing chemistry. No chemistry is happening when the electricity passes through the wire to my computer and then back to the power company. So conductivity is just a physical phenomenon, but chemical reaction where the matter actually transforms is different. So how are we going to draw these compounds? We're going to draw them with Lewis structures. So the whole point of yesterday was to get us to get into the habit of doing stuff like this. Except we're going to make these really, 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 really long. That's the wrong button. By doing stuff like this. Do. And you can see just how obnoxious this is going to get as we go. And I'm going to actually draw this whole example here. Not because I don't respect your time, but because I want you to see that, like, wow, to draw this 9-carbon molecule took like a minute. That's going to be really obnoxious. How the hell do I put that into Canvas? Yeah, exactly, right? And then it's gone. So, you know, what can you do? All alkanes involve single bonds only. Okay, so that's going to be our very important distinction here. We're going to have only carbons and hydrogens, and all of the carbons that are linked together will have only single bonds. An alkane that has only single bonds is called a saturated hydrocarbon. What that means is that it has the most hydrogens it can have. Later on, we talk about alkenes, which have double bonds. Note that I said alkane versus alkene. When we have double bonds in the molecule, we replace hydrogens with a double bond. And those will be unsaturated. So we're going to see that later on. Now, alkanes are sort of the backbone or template of all molecules. So everything starts with alkanes and then builds from there. So we're going to change out atoms to get other molecules, but our template is going to be the alkane. Later on, we're going to talk about functional groups. Don't worry about functional groups right now. Right now, all we care about is this carbon and hydrogen chain. Now, why do we care about alkanes? And the answer to that question is, I'm going to draw an alkane. I'm going to draw a shorter chain alkane. We're going to draw butane here. And yet, still takes a long time to draw butane. So, if I drew this molecule in Chem 121 and I said, tell me about its intermolecular forces, what can this do? You would look at this molecule and you would say, okay, well, is it polar? And we said any bond that is not XX or CH or CS, these are all nonpolar. So we would conclude that this molecule is essentially nonpolar, and so that the only intermolecular forces it would have would be dispersion or London intermolecular forces. Now, if something has dispersion as its only intermolecular force, what that means is that here's my molecules here. These are held together by very, very weak interactions. All alkanes are nonpolar, yeah. Now, substituted alkanes are not nonpolar. And you'll see what I mean by that later on. But for now, anything that has only C's and H's in it, nonpolar. Totally nonpolar. So with these very weak interactions from dispersion, these molecules are not held together very well. And so that's going to have consequences later when we talk about boiling points. But what can we use these things for? Having very weak interactions is actually beneficial in some cases because we can have molecules that easily slide over each other. And so we use alkanes as things like lubricants. So a lubricant would be used to prevent two engine parts from grinding against each other and causing friction, which would heat up the engine to the point where it might break down. We can also use them as things like solvents. So solvents are liquids that other things dissolve into, such as, say, in salt water, water would be the solvent. It dissolves the salt in it. We could use alkanes to dissolve other things. For example, grease and grime. This is actually the premise by how soap works. Soap is mostly an alkane. There's a non-alkane part. There's a carboxylic acid part to it. But we'll talk about that when we get to biochemistry. Now, cell walls and cell membranes are also mostly alkanes, and that's going to make all of this very useful to understand. Yeah, this is why you can't mix oil and water. Oil and water are immiscible. They separate out from each other because oil is mostly alkanes. Now, we can't call oil an alkane specifically because what oil is actually called a fat. And what fats are long chains of alkane hydrocarbons connected to a very polar part. And we'll get to that in chapter 17, I think, is when we do lipids. But yeah, so you'll start to understand all these things that we just sort of told you in Chem 121. It's like, oh, that's why. And it has to do with alkanes. So understanding alkanes is really useful. How many of each atom are in an alkane? Here's the formula. Remember when I said that you don't have to use a calculator for this class? This might be the one exception. So the formula for an alkane is this: CnH2n plus 2. N is the number of carbons. So you could pick any number you want, multiply that number by 2, and then add 2. And that's the number of hydrogens in an alkane. Down at the bottom, I have some simple calculations for the first few hydrocarbons. I'm going to have you do a few on this next page in a second. But for example, methane has 1 carbon, so this would be C1H. 2 times 1 is 2, plus 2 is 4. So that's how you get CH4. Ethane is C2H. 2 times 2, which is 4, plus 2 is 6. Now, if I was to draw this out with Lewis structures, I don't really have a good way to do that. Let me try... Oh, no, duh. I'm making this hard on myself. That's what this is for. Oops, my Photoshop didn't like that. Hold on. For some reason, when I minimize and maximize it, it freaks out. All right, so let me put this on the screen since this is what we're talking about. Oops. I'm holding down the button. I don't want that. All right, so if we have methane here, so here we go. C... And you'll notice that there are just 4 positions because carbon can only form 4 bonds to make its octet. There we go. There's our methane. But now what I'm going to do is I'm going to make ethane, which would be this formula here. So I'm going to go C2H6. Now watch what I'm going to do. I'm going to take the cut tool and I'm going to cut this part. And we're going to move it over here. Oops. No pixels were selected. Yes, I'm aware. And then what I'm going to do is I'm going to add in this part. And so that's how I get C2H6. So each time I add a carbon, I also add 2 hydrogens. Now I could do this again. So we'll take this guy, and we'll just move him over. And oops, I got to select none there. And I'll just do the same thing again. And this would be C3H8, which still follows the CnH2n plus 2 formula. And we'll just do this forever and ever and ever for as many carbons as we want. Now, I'm drawing those molecules flat on a paper, and I'm not even paying any attention to geometry. We are going to want to consider geometry to some degree in this class. And so what we'll do to do those considerations is we're going to make models out of this. Our first lab next week on Monday is going to involve creating models of alkanes and also alkenes and alkynes, which you'll be introduced to over the course of chapter 12 and 13. It's very difficult to make a model on a 2D screen. I have a program available online. I've found one, I should say. But it doesn't replace like having models in your hands. So what I'm going to try and do is find pictures of these molecules as models and do the best that we can here. On the screen, you'll see 3 different ways that we're going to represent these molecules. So this first one here just draws everything with 90-degree angles. And then this one cares about geometry. These two together are representations of the same sort of geometry in space. We're going to talk about what those wedges mean later on in more detail, but for now, what you can do is you can visualize that this wedge means that it's coming out towards you. And this wedge means that it's going into the screen. Isn't that second one acyclic? Not sure if that's a typo. Acyclic, okay. Acyclic means it does not form a circle. So we don't have a ring of atoms. So technically, yes, but we haven't even gotten to cyclic compounds yet. Anyway, that'll be the end of chapter 12. Now, as we saw before, these chains are going to extend in all directions, but because of this geometry, what I drew over here in the sample problem window is kind of a simplification. So these atoms are in a chain, but they aren't in a straight line. So that's something that we're going to have to consider when we make the molecule. And we'll come back to that in a little bit. Now, the geometry of this carbon, its Vesper and molecular geometry, we really only care about molecular geometry. Because there are 4 things connected to that carbon, and none of them are electron pairs. This carbon is in a tetrahedral arrangement. And what that means is that all of these angles between any 2 pairs are equivalent. And they are all 109.5 degrees. Notice that over here, these are all 90, so that this diagram does not show the correct geometry. So this is an incorrect geometry. Incorrect geometry shown. Sorry, my handwriting is not great in PowerPoint for some reason. Like, it doesn't register everywhere that I put the pen, and it tries to just improvise. If you can't read something I've written on the screen, let me know. My handwriting is much better in person. I would guarantee that. All right, so that's methane. That's the first simplest alkane. From there, we would go to ethane, where we just add an extra carbon and 2 hydrogens. And then propane would be 3 of those. Now, these names that we're giving these, methane, ethane, and propane, these are just common names. You will have to commit these names to memory, because we will be using them throughout the quarter, but you will get that habit very quickly. You're going to be using methyl and ethyl and propyl so much that it will just become second nature. And as alkanes get longer and longer and longer, we just continue the pattern. And this goes forever. You can have alkanes with hundreds of carbons all lined up. Yeah, this is the homologous series. Is all of these follow the formula and you just add CH2. I think that's going to be the next slide. One of these slides here talks. There it is, right there. So that's how we get to that. Oh, we'll get to that in a second. Yeah, that's kind of a confusing statement in the book. But what the homologous series means is that this is just a series of molecules that differ by a common unit, and that unit is this right here. So I could just add, I can copy that and go paste, 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 and every time I paste, I make a new member of the homologous series. What I need to do now, and I should have thought to prepare this earlier, is I need to go to mol view. We're going to use mol view a bit this quarter, because I have found it to be super useful. I was going to talk more about this in the lab, but actually what we'll do, let me window capture. So let's talk a little bit about mol view right here. Oops, I got to make this smaller so that I can find out where the boundaries are. There's the top, and there's the bottom. This is caffeine, by the way, if you were just curious. I'm going to cover the chat a little bit because it makes it a bit bigger. So this is caffeine. What we're going to do is we're going to get rid of it. Boop. And what I'm going to do is I'm going to draw methane in here. So I'm going to put... That's not what I wanted. We're going to do that. And we're going to do that, that. Make them all hydrogen. I'm going to make the structure nice, so it's going to straighten that out for me. And then I'm going to make it 3D. So it's going to make a model of what I just made. So here we go. Here's my methane. So I'm going to spin it around. You can see in 3 dimensions that this is what it's like. You can do this sort of thing too if you'd like. Let me put the link here. Actually, there you go. So you can construct molecules all damn day if you want to. But now what I'm going to do is I'm going to take this. I got to zoom this out. How the heck do I zoom this out? Oh, there we go. Okay, it's just like Photoshop. So let's move you over. I'm going to turn this guy into a C. And I'm going to go boop, boop, boop. I'm going to turn these into H's. I'm going to tidy up. And then I'm going to make the model of it. So you can see from my Lewis... Oops, I didn't mean to actually click there. Oh, no. Oh, no. Come back. There we go. So you can see from my model, everything is at right angles, but in my molecule over here, there are no right angles. Everything is tetrahedral. And so this is what my ethane molecule looks like. Now, because each time I am making the molecule longer by basically taking this atom and going boop and turning it into a C, and then putting that H on the end here, which scrolled off the screen here. Oops, I don't want to move that. I want to move the whole thing. What's actually happening here, we'll tidy up the structure, is we're going to replace one of these 3 hydrogens on this side with this CH3. And what's going to end up happening is we're going to start making this zigzag pattern. So when I convert this to 3D, now I have a zigzag here. And if I were to do this for a really long structure, and I'm going to get rid of this, we're going to go like this. Do. There we go. So we'll draw 9 of them. And I'm going to fill the rest of it in with H's. So oops, that's not what I want. I could do it this way, though. Ah, no. There you go. Oops, that's not right. That won't work. I messed up one of these, and now it's going to make me do it like this all the way across here. There we go. So, ow. I want to move the whole thing. So tidy up. And then make a model. And you can see that this is just, it's really zigzaggy. And I can spin this around all however I want to. And this is how alkanes work. So you can play with this all you want and spin it around. I think this is a super useful tool. And it's also fun to just kind of go, wee. But it really helps you understand what the geometry of the molecule is and how these things look like. So we're going to be using this a whole bunch this quarter to try and visualize how these molecules look like. So even though we're going to be drawing these structures on the screen like this with 90-degree angles, remember that because all of these centers are tetrahedral, we're going to get that zigzag pattern that you saw there. And that's going to be really helpful to realize because seeing that it's a zigzag pattern, we'll put it back up here, it's still kind of linear, right? And if a molecule is really linear and has a very large surface area like this, it's going to be susceptible to interactions like dispersion. And so this is actually the premise behind cell membranes, which we'll get to later on. Now, what happens if you don't put your carbons in a row? For example, here I have all 4 carbons in a row, and they're just connected one after the other. But I don't have to do that. I could put my carbons in different positions. So instead of going in a straight line, I could go both directions. If I have 4 carbons, there's no reason that I can't do this and this. If I had 5, I could put the 5th one there. Or I could put it here. Or any number of places. Some of them would actually be the same, but most of them would give you a unique sort of arrangement. And we need to consider these possibilities too. So what we're going to do is we're going to say if all the carbons form one contiguous line, we're going to call this linear. Now, as you saw in the picture, these are not linear molecules. They're zigzaggy. But linear means all the carbons form a straight chain. We'll worry about isomers in a second. That was something else I thought. If you try and make a chain and a branch occurs, we're going to call it branched. Now, how many of you have played Settlers of Catan? If you have, you know how there's a victory reward for the longest road? And the longest road is just how many pieces can you draw in a straight line through the game board? And whoever has the most color pieces of their color in a road, it gets the victory points for that. In alkanes, we follow the same sort of thing. We have to find the longest chain. You don't get any points for it, though. It's just that when we talk about an alkane, we're going to be caring about the longest chain. And so what we will do for that is we are going to count the number of carbons that are in a row and then indicate that. In this left thing over here, we've got 4 in a row because I can go 1, 2, 3, 4 and count in a straight line. Over here, I can only do 1, 2, 3. In order to do 4, I would have to be connected to 3, but it's not, right? So this is not part of the chain. In this example, there have been 2 different ways that we can draw butane. I can draw 4 in a row, or I can draw 3 and then branch off from the middle guy. When you have multiple ways to draw something, we call those isomers. So these are two isomers of butane. And their structure will be different. So for example, if I go back to mol view, let me draw the molecules really quickly. In fact, I wonder if I can do two of them at once. Let's see if I can. I'm just drawing the structure really quickly here. Ah, no. I don't want you to see my failure as I draw the structures here. Okay, so there's butane. And then I should be able to just copy this part and paste it down here. Oh, I can't copy and paste on this. Okay, never mind. I'm wondering if it'll let me draw two structures. H. Alright, tidy up. Oh, it totally did. Can I make two models? Well, I can. They're not exactly where I want them to be, but that's okay. There we go. Okay, so can I rotate this around? There we go. That's what I want. So you can see on the screen here, I have made butane on the top here. And it's linear. Down here I have the branched guy. And if I spin them around, you can see that this bottom one is kind of round. Whereas this top one is kind of long. So even though they have the same formula, they have different shape. And as a result of that, they're going to have different physical properties. In fact, we're going to learn that this one has a higher boiling point, and this one has a lower boiling point. Why? We'll talk about that in a little bit. But what's important is by drawing the Lewis structure differently, we get a very different shape. And we'll explore that in more detail later on. This is the homologous series, so we talked about how if we add CH2s, we change the molecule. Again, what a homologous series is, and this is the only time this word comes up, so I don't even know why we teach it to you. A homologous series differs by something that you can copy and paste. And so in this instance, I copied this, and then I just pasted it right back in. And so you can do this forever. So let's do some examples, and maybe not draw the structure. Well, actually, I want you to draw the structures of some of these. It is going to be tedious, but that's sort of the point for this first lesson, is I want it to be tedious so that you adapt the better method that I'm going to show you later. So for this first example, let's draw an alkane with 7 carbons and determine its structure. And so what we'll do is we'll go to the sample viewer. I didn't capture the problem statement here. I want 7 carbons, and so what I'm going to do is I'm going to go like this. I'm going to just move this guy aside. And I'm going to copy... Oh, that's not going to work. Hold on. I'm going to copy this part. So I'm going to go copy, paste. 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 And that should be 7 carbons. 1, 2, 3, 4, 5, 6, 7. Now all I got to do is I just got to get this guy. The selected area is empty. Oh, right, because I made like 75 layers, didn't I? How do I merge layers with a keyboard? I can't. I had to do that. Okay. There you go. So that would be a molecule with 7... Oops. I have a pixel selected. That would be a molecule with 7 carbons. How many H's would there be? There would be 2 times 7 plus 2 of them, or 16. Now, of course, you're not going to be able to copy and paste on your pad of paper. If you do, that is a badass pad of paper, and you should keep that. But if you draw this all out, it's very straightforward how to do it. Now, what is the geometry at all of these centers? Let's suppose that we wanted to actually draw this with a more three-dimensional representation in mind. What we would then do is we do something like this. So carbon, carbon. And what I would do is I would retain that zigzag. So there's my 7 carbons. And then I'm going to just put the other hydrogens on the other points here, so that everything kind of looks like it's 3D. And really, the point of this is to get you out of the habit of drawing everything in right angles, because we do want to consider what the geometry of the molecules is. So that would be heptane. Heptane has 7 carbons in it. We'll talk about the names in just a little bit, too. All right, so we're going to do one set of practice problems here. I just realized that the example that I did right here and then the example that you're going to do right here are exactly the same. I might have to change that, but that's okay. What I want you to do is for these 3 things right up here, I want you to predict the formula. You'll notice that this is absurdly stupid. Like, this is just, hey, can you plug the number in the formula? You might have to use your calculator for that. And then I want you to draw these pictures. We have already drawn this one, so you don't need to do that. But on any sort of paper or computer or whatever it is that you have handy, draw the structure of octane, which is the alkane with 8 carbons. Okay? Then predict its formula. Maybe predict its formula before and after you draw it, and see if what you draw matches up. Okay? So I'm going to give you a few minutes to do that. Type your formulas in the chat when you are done. And then once we've gone over the answers, we'll take a break for our hourly break. Okay? See you in a bit. All right, 1 or 2 more minutes and we'll go over the answers. All right, so let's use that formula. We'll write it up here at the top. So CnH2n plus 2. So if I have 6 carbons, that means that this would be C6H. 2 times 6 is 12, plus 2 is 14. So that's hexane. If I have 20 hydrogens, then what that means is that this right here must be 20. So 2n plus 2 equals 20. And holy crap, we're doing algebra? I thought there wasn't going to be any math. Yeah, that's just to let you know that algebra is a useful skill. As much as we don't want it to be, it's useful. And then this is just, can you punch it in a calculator? Sure. 217 times 2 is 434, plus 2 is 436. I think that's right? Everyone else is typing that, so it must be. And then an alkane with 8 carbons. Why didn't I make this in mol view while y'all were working? I don't know, but hold on. Let me quickly make this molecule in here. Can I do 5? Can I, if I hit this button, will it fill in hydrogens? It will if I didn't have a hydrogen already there. 1, 2, 3, 4. Cool, okay. So now I can go back to mol view. Here is my 8 carbon chain. This is what its Lewis structure looks like with the zigzag. Here's the molecule itself. I don't really know what direction you would like me to rotate it around, so I'm just sort of panning it around randomly here. And there you go. So that's our very introductory overview of alkanes. So when we come back, we're going to move on to the next section, which is to talk about what branches have to do with all this structure. But we do get a break. I don't have the timer out. Let me get the timer out here. I'm really reluctant to say, please don't read the news during the break, because everyone's going to immediately go read the news. But if you don't want to be disappointed, don't go read the news. See you in 10 minutes. I'll put some music on. Just listen to that, and we'll try and stay focused on what's going on here and not in the outside world. See you in a bit. Yeah, I will be so close every time. Like, I'll get within 1, I'll get within 2. I've landed exactly on it twice, and I've had, like, what, 100 times to do it? I mean, well, just a second. Let me just hit mute. It's a really good one. That's really what I can say about it. There we go. It was, so we have a midnight cookie company around here, and last night at like 8 p.m., I was like, I have to have cookie. So I went out in the pouring rain. I went and bought a dozen cookies of various types. And the one that I just had right now was a coconut. It was coconut, but it was like a really fluffy, thick cookie. Yeah, I definitely got 2 birthday cake. I haven't gotten to them, though. I have to dig through all the other cookies that are on top. And they're all so good, so. Let's go back to mall view. Let's go back here. All right, so we spent the first hour talking about a very general overview of alkanes, and I introduced you to some of the names of them. Now what we're going to do is we're going to talk about different ways that we can name the alkanes for a longer chain, so like the IUPAC names for them. That'll come back down there later. And also about branches and stuff. And then finally, where we're going to culminate that with, in this section down here, 12.4, is we're going to show a bunch of different ways to draw these. And we're going to stick with one of them in particular because it is the most useful. And if we spent the rest of the period just learning how to do that, I'd be okay with it. Because it's the most important skill for this chapter, is learning how to represent these pictures with those stick diagrams that you've probably seen up there. Let's look at some examples with pentane. So pentane has the formula shown here, C5H12. There are 4 different ways to make pentane. They all have the same formula. Here's all of my carbons in a line. That's the simplest way, but there's only one way to do that. And then there are 3 unique, or I'm sorry, there are 3 ways to do this. There are 2 unique ways to do this. I can go 1, 2, 3, 4, 5 like that, or I can go 1, 2, 3, 4, 5 like that. And oops, that's not the button I want. I want clear. There we go. There are the other ones right there. Now, if you'd like to, you can put those in the model viewer. I actually learned. I was playing with the model maker while we were taking a break here. And so let me just clear everything. If you just click on carbon and then you click this guy, you could just go 1, 2, 3, 4. Well, I only want 4 total. And then I'll just put 1 here. And then I will hit 2D to 3D, and it'll fill in the rest of them with H's for me. So there it is. That takes way less time. And I heard my cat. Sorry. My cat loves to come in and say hi. So there's that branched one. And then what I could do is I could take this and go boop. Oh, I erased the wrong one, but that's okay. So we could go like this. And we can generate this one. I should just hit don't show again here, huh? There we go. All right, so those are all pentanes. Those are all unique ways that we can describe pentane and construct a formula for it. Now, we're going to want to ascribe some different properties to these. On this slide, I have removed all the hydrogens just to show the chains here. So I got my linear version on the left here. Oops. And I got my branched ones on the right. So a linear chain will allow us to number all the carbons sequentially without having any place where two numbers that are not adjacent to each other touch. So in these cases, I have circled where non-sequential numbers are adjacent, indicating a branch. Now, obviously, visually, you could just look at it and go, oh, it's branched, it diverges. And that's the best way. But if you wanted a formal definition or a formulaic definition, you could use this, where I number all the carbons in a straight line, except when I can't, and there's no way that I can number them, even if I change these guys around. So what if I put the 4 up there instead? Well, then I got to put the 5 in the other position, and then this becomes the fault. So there's no way to number a branched alkane where all the numbers are adjacent to the next number sequentially. All right. How about this? Notice that I have drawn the structure on the screen like this. Is it linear or branched? Well, using the same philosophy, I would just number the carbons, like so. And at no point do I have a number that is not next to the next number sequentially. 3 is next to both 2 and 4. Those are both sequential numbers from 3, whether you're going down or up. So even though this has a kink in it right here, this molecule is still considered to be a linear molecule. So again, remember that we really just care about the chain of carbons when describing something as linear. On the next few screens, I'm going to try and contort these into all different directions. And what your job will be to do is, I might have this snake thing going on. And I'll be like, is it linear? And you'll be like, 1, 2, 3, 4, ... I don't know how many there are there. Wow, I actually counted that correctly. Okay. You'll be like, yeah, you can number them all sequentially, and so it must be linear. You've just sort of bent it into this sort of crazy shape or whatever. Now, it's for this reason that there are only so many ways to draw C5H12. And you might think to yourself, well, wait a second. Couldn't I do it a fourth way? Instead of putting the branch on the third carbon, I could do it on the second carbon. And I'm going to show you why that doesn't work. So first we're going to clear everything. And then what I'm going to do is I'm going to draw... So here's our default chain. So this is the first way to draw this. And we said that there was another way to draw it where I take 4 of them and I just put a branch somewhere. And then this was the third one. And I'm going to propose, hey, let's go like this instead. Is this different from these? It sure looks different. And the answer is going to be no. This is actually a duplicate of number 2. And I'm going to show you 2 ways to verify this. So the first, we're going to... Oops. I got to unselect. There we go. I got to select this guy. And what we're going to do is we're going to go copy, paste. That's not how we do that. There we go. And then what I need to do is I got to go into Photoshop, and so edit, transform, and I want to rotate. No, I want to flip vertical. That's not right. I always mess this up because it doesn't make sense to me. I want to flip horizontal. There we go. So you'll notice that all my C's are backwards now, but if I go like this, they have the same structure. So this molecule over here, number 4, can be rotated 180 degrees around this imaginary axis that we'll call it. So if I rotate this 180 degrees, I would get that, which is actually the same thing. Now, the other thing that we can do Oh, I gotta merge these layers. Hold on. The other thing that we can do, let's just clear all here. Boop. Is I can number the carbons. So I'm going to 1, 2, 3, 4, 5. Now, if I have a structure and I can number the carbons in the same way in both structures, they are the same structure. Now, can I get a structure numbering over here where it's all sequential and 3 touches 5? I can if I start number 1 over there. So, number 4 and number 2 must be the same. And so this method is called the numbering carbons method. It's not very technical. But what we're going to be doing is we're going to be numbering carbons to identify whether two drawings are the same or are unique. And so that's the objective of this. Now, regardless of whether they are the same or unique or whatever, drawing the molecules in a different orientation is called a conformation. A conformation would be, okay, here are my carbons in a row, or I could conform them to this orientation, or I could conform them to this orientation. They all have the same connectivity. If I went and numbered the carbons, I would go 1, 2, 3, 4, 5 on every diagram. But if these were spatial drawings of these molecules, they would be different positions in space. And so we're going to call these different conformations just to indicate that our molecule is, these are still the same molecules, but these are different, like, pictures of them. They're in different states. Kind of like, it would be kind of like if you stood up from your seat right now and took a picture. Then you sat down and you took a picture. Both of them are pictures of you because you are the subject in the picture. But you sitting and you standing are different conformations of your body. Just like these are different conformations of the same molecule. All right. Now, why do we care about conformations? We care about conformations because molecules exist in 3 dimensions. They spin and move and rotate. Anything that has a double bond or a triple bond won't rotate, but single bonds do rotate. We're going to talk more about this in the lab next week. Actually, you know what I should do? Let me get rid of this H here, and I'm going to put a different atom here. We're going to put a different color for that. Let's do Cl. Now, if I were to take this bond and I was to spin it around, because single bonds can rotate, what would then happen is that all of these guys would rotate around too. And the consequence of that is that if I rotate this guy, the Cl would then be in the down position, or the back position, or the top position, based on where it rotates to. And I show that right here, so let me hit clear. So here's my chlorine. I often forget what illustrations I have already put in here. These guys can rotate as this rotates around too. Now, if every single bond can rotate, don't we care about other bonds? Like, what about this rotation? Doesn't this matter? Well, it does rotate, but this is, since this is symmetrical, it's just H, that H is just going to rotate around, kind of like a marshmallow on a stick, because nothing is connected to that marshmallow. It doesn't really change as you rotate it. So we don't really care about end point things. But in the middle here, I have this whole cluster that rotates, and there's something on here that makes it not symmetrical. And so we do care about this. So these are different conformations of the same molecule because they have different orientations of their atoms in space. All right. So let's start looking at some structures here in different notations. And we're going to try and determine, are they the same molecule or are they different based on what you see. Now, you'll notice that the structure on the left, all the H's have been expanded. On the structure on the right, I threw it into ChemDraw and it condensed all of the things down to just these terms. So like CH2. Yeah, but you can change the conformation by just moving any part of it. Kind of like if your body is your conformation, raising your arm up like sideways would be a conformation. Then raising your other arm so it was like at a 90-degree angle so that you're sort of doing like Pilates would be a different conformation. Then bending forward would be a different conformation. And so any orientation of your body in space is a unique conformation. Just like any orientation of the molecule is a unique conformation. Now, the reason that we care about conformations when looking at two structures is because the possibility that they are the same exists. So these two pictures are obviously different looking, but are they the same molecule? And the way that we'll do that is by numbering the carbons. So let's number the carbons. Let me get a different color out here. Let's do purple. So let's do that. 1, 2, 3, 4. And if I can number the carbons in the same way, then they are the same molecule, just in different conformations. If I couldn't number them the same way, they would be unique. All right, so there's my numbers. They're just popping up. Since I numbered them the exact same way and everything touching those numbers is identical in both cases, they're the same molecule. They're conformers. Now, later on, when we start adding more stuff to this, I've already worked on the assumption that there's just H's, but we're going to care about what's touching what. So 1 needs to be a carbon that has 3 H's on it in this case, and if that is the same over here, then that's good. And then 2 would be a carbon touching 2 H's. That checks out. 3 is a carbon touching 2 H's. That checks out. And so on and so forth. So we've sort of been glossing over the more technical way to interpret these, but for our purposes, that's fine. So now I get to show you a bunch of molecules and say, are they the same or are they different? So here's 2 molecules. Are they the same or are they different? Type in your answer in the chat and let me know. And then we'll go over the answer together. All right. Everybody thinks they're the same. Let's see if you're right. So if I number these like this, you'll notice that I've put this little like apostrophe thing here. The apostrophe just indicates, hey, there's a branch there. So if I can force the branch to be on carbon number 2, in both cases, they must be the same molecule. And they are. They're both pentanes with the CH3 branching off position 2. How about these 2? Are these the same molecule or are they unique? What do you think? Very good. They are unique. Now, how do you know? How do you know that they're unique other than just like, oh, they look sort of different? The answer is you would number the carbons however you wanted to. So I'm going to number them like this. And then what I'm going to do is I'm going to take the pen. And it is because of that, yes, because the CH3 is in a different spot. I'm going to take the pen and I'm going to number each one backwards. Because our orientation doesn't matter. We can number things however we want to as long as they're in a line. And so over here, in both cases, I get 3. Over here, I never get 3. There's no way to number it to get 3, so these must not be the same. The branch is in a different position, and I just can't number them the same. There's no possible way to do it. Now, remember, this is all based on we have to number them in the chain that is the longest. Just like we identified earlier, where we're numbering the longest chain possible. All right, we've got more of these. How about this one? Same or different? I don't know why I put so many examples of these in here. It's good practice, though. Yeah, these are the same. Very good. And then how about these? Oh, it's getting more complicated now, isn't it? Same or different? I'm going to put a mark in the chat here. I'm just going to do that. And so answer after that one. Are these the same or different? You need the examples. Can you be more specific? Oh, or are you just commenting that, like, the more examples is helpful? Okay. I mean, they sure look different. What have we been doing so far that would tell you? Can you number to go over again? Sure, we could do that after this one. We'll go back to that one. What were we doing to identify whether they were the same or different? We were numbering something, right? All right, so here's our hint. Find the longest chain. What's the longest chain on the left? I'm going to say that it's this one. 1, 2, 3, 4, 5. What's the longest chain on the right? Well, it's got to involve this part. 1, 2, 3, 4. And then if I go up, I can get more. 5, 6. So can something with 5 carbons in a row be the same as something with 6 carbons in a row? And so now you should immediately be like, oh, okay, it's different. And that's correct. In this case, I don't even need to number them in the reverse direction because they just have different numbers of carbons. 5 and 6 is always going to be different. Could the order indicate they're different as well? Well, we don't even need to get to that point because they just have different numbers of carbons. You could also say, oh, the branch occurs on 2, but it occurs on 3 on the other one. So that would help you. But the easiest way to differentiate them would be, oh, they have a different number of carbons. A student requested to go back to this one, so I'm going to number these carbons. We'll go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now, you could go backwards, but there are no branches, so it doesn't super help you to do that. But in both cases, I was able to get a 5-carbon chain, and all the numbers are connected, so they're both linear pentane. Therefore, they are both the same molecule, just in different conformations. All right, let's go to the examples that I have you do. Here you go. I want you to tell me if each pair is same or different. So the line in the middle separates the two. So this is problem number 1, and this is problem number 2. And so I want you to tell me if in group number 1, are those the same molecule, just different conformations, or are they unique? And then do the same for number 2. So I'll give you a few minutes to do that. Remember, number the carbons, find the longest chain, and then see if you can number backward and forward for any branches. All right, let's go over the answers here. So I'm going to start on the top position here. I'm going to go like this: 1, 2, 3, 4, 5 to number the longest chain. And I'm going to call this one over here, we'll just call it star. So 3 and star are next to each other. Now, if I number it in the reverse direction, we'll get that. And that's just going to be for our reference when we go over here. So now I'm going to go 1, 2, 3. I don't know what happened there. I said 1, 2, and I wrote 1, 1. 1, 2, 3, 4, 5, with a star next to the branch. And you can already tell that, oh, In every way that we've done this, the branch occurs on number 3. And if I were to number this one backwards, the same thing would happen. So these two must be the same molecule in different conformations. All I did to make this molecule in the bottom here was I took this bond and I just rotated it around. How about this one down here? So we'll number them left to right. 1, 2, 3, 4, 5, 6, 7. And the number here we'll number left to right. Uh-oh, we ran out of carbons. So this one we got 7. This one we got to 6. They must be unique. So again, our identification rubric is going to be 1, count the number of carbons in the longest chain. If they have the same number of carbons, then we would check for where branches occur. If branches occur in the same position, no matter how you number it in both directions, on the different orientations, they will be the same. How we do this? So it's on the previous slides, but we can summarize. Let me summarize over here, though, because I have more space here. So, oops, let me get the black marker. So step 1, we want to check the longest chain. And then at step 2, if they have the same chain length, then check for where branches occur. And at any point, if you see any differences, then they are unique. But if you do all of this and you get the same carbon counting, then they are just different conformations of the same molecule. Oh, I think my cats are fighting now. I heard them I could hear them through the headphones that I'm wearing. There you go. Yeah, no problem. All right, let's talk about some terms that we can assign to these before we call it a day, because we only have a few more minutes left. Now, in one of the previous examples, we had a branch occur in a different spot. I think if I do this, the numbers... Oh, they don't pop up. Okay. I'm going to number them again then. So here's 1, 2, 3, 4, 5. Here's 1, 2, 3, 4, 5. And so our branch occurs at a different spot in these molecules. Now, if I were to write the formula of these alkanes, the formula for both of these would be C6, because there are 6 carbons, H14, because 6 times 2 plus 2 is 14. And you can check that if you want. So 3, 6, 7, 9, 11, 14. So they're all there. These are 2 different ways to make C6H14. Now, we said, okay, if there are 2 ways to make them, they're called isomers, but there are all sorts of different types of isomers. The first type of isomers we're going to talk about are structural isomers. Structural isomers, which you might also hear called constitutional isomers in different textbooks. Anything that has same formula, different branching, is a structural isomer. In other words, I moved the branches around. That's how you get a structural isomer. You changed the structure. Now, keep in mind, I could have moved the branch over to here and had a 6-carbon linear change, and that would also be a structural isomer of the two that are on the screen here. So on a quiz or exam, what I might ask you is I might throw 2 pictures up and I'll say, are these structural isomers, or are they different conformations, or are they unique? So for these two on the screen here, what you would say is, oh, they are structural isomers. The branches are at different spots. Whereas for these two, let me clear the screen right here. If I asked you about these two, you would say these are different conformations, and then these down here, I lost my cursor, there it is. These down here would be unique. All right. Now, let's suppose I wanted to draw all of the possible isomers. Wouldn't say structural isomers for which ones? Sorry, I think I was behind or ahead there. Let me just clear that off the screen there real quick. No, because different conformations have the same connectivity, whereas structural isomers have different connectivity. So again, if I number these right here, the branch always occurs at 3. So these aren't different structures, they are the same structure. I have just spun this guy around to a different conformation. No problem. All right, so over here, what we're going to try and do is we're going to try and make all 5 possible isomers of C6H14. I've already done 2 of them. So I'm going to number the carbons. I'm writing over hydrogens here, I'm sorry. And then we'll put a star here for our branch. And on your paper, I want you to spend like a minute or two trying to just push pieces around and make unique structures. Now remember, you could number backwards. So if your first thought was to say, oh, I'm going to take the CH3 and put it on number 4, then what will happen is you'll be in this situation down here, where I could just go 1, 2, 3, 4, 5, and now it's the same as this one. So you had to be a little more creative than that. I didn't mean to erase everything. So take a second and try and identify the other possible places you could put branches. And I'll give you a hint. You don't have to have a branch that's only CH3. You could have a branch with a CH3 connected to another CH3. Or maybe you could have more than one branch. What possibilities are there? Try moving some pieces around. And I'm going to go over the answer with you on this in about 2 minutes. Okay? All right, so let's try and draw some of these isomers. So there's the first two up there. We're going to see how creative you got with this. All right, so the first and most obvious one would be to just put everything in a line, because that wasn't one of the ones that was listed. So this would definitely work. Now, I can fill in the H's, I guess. I'm going to skip this for the remaining ones just because I'm trying to do this a little more quickly. Now, we've got this one for 5, where the branch is at position 2. If we did the branch at position 3, that one we've already gotten to. If I put the branch at 4, that's like me putting it at 2, just rotating it around. So that leaves, what if I put the branch at position 1? Well, that's just a confirmation of this guy up here. So that doesn't work either. So we have exhausted all of the possible isomers, structural isomers, for a 5-carbon chain. So the next thing to do is, well, let's get a 4-carbon chain going. Let's see what we can do with that. And so that would require us to put down 2 more carbons. So I'm going to put a branch here. And then I'm going to put a branch, well, if I put it here, that's now a 5-carbon chain, so I can't do that. If I put it over here, that would also be a 5-carbon chain. So I got to put it on one of these two. I'm going to do this. That's unique. That is 6 carbons. Here would be our H3. No H's here because I've already got 4 bonds. CH3, CH3, CH2, CH3. So that would be unique. And then, let's go back to the 4-carbon chain here. I'm going to put this one up here, and then I'll put the next one. Well, if I put it here, again, I have a 5-carbon chain. So that won't work. We've already got all the 5-carbon chains. So what I'm going to instead do is I'm going to put it over here. And that will be unique because if I number these guys, I have both the branches on number 2, but over here, I have 1 branch on 2 and 1 branch on 3. So those are our unique isomers. Now that's intended to be a difficult problem, so don't feel bad if you didn't identify all of the isomers. That's okay. The whole point of this exercise is to get you to visualize in some way how moving around all of these pieces can be done, and it's a lot easier if you have something tactile. Like if you had a model kit, we would do this example in the classroom, and I would, oops, I didn't mean to click that. I meant to click this. It'd be much easier to move the pieces around with your hands because you can see it in front of you. On paper, it's different. But what I want you to try and do with these exercises in this section is to imagine moving these pieces around. Play with the mall view. I don't know why that car alarm is going off outside. That's just great. Play with the molecular viewer and see what you can do with this. So you could draw that as your structure. And what you can do is you can draw different things. Let's clear everything real quick. And say, hey, are these the same thing? So I'm going to draw this. And then I'm going to draw this. And so I'll convert them to 3D. And then I'll zoom this out. And then I'll say, are they the same thing? They look pretty similar to me, right? Because I got 5 in a row and then 1 coming off, 5 in a row, 1 coming off. The H's are going to go in different directions based on how I rotate it around, but they do look very similar. Okay? And that's going to help us a little bit. All right. Oops, that's not what I meant to maximize. Where am I? I think that's all I have here. Yeah, so let's really quickly talk about what molecules really look like. As you've seen in the model viewer, and this is actually where I stole this picture from, all the angles are going to be 109.5 in the models. But in our Lewis structures, when we've been drawing them as 90. So these are not the correct angles. So these are wrong angles, but simple to draw. These are the correct structures. That's not the letter U. These are the correct structures that are observed. So again, you can draw your Lewis structure however you want to, but it's very important that you don't miscommunicate to yourself what the structure looks like, okay? So always remember that these carbons are tetrahedral. And that's it. That's all we got for today. I already went over by a minute, so. I want to thank everybody for coming out to the lecture. If you have any questions, or if you get that Discord set up, or if you want me to know anything, whatever, like send me an email. I'll be around all weekend. The next class period that we will meet will be on Monday, week 2, where we will go over a lab and then review any of the content. So with that, I want everybody to have a wonderful weekend and stay safe out there because things are getting crazy. So be careful, stay safe, stay healthy, stay at home.